Starting at 18 in the section 5.7 Achieve assignment, starting off with a really good problem here. So again, this is the substitution problems. For this one, we have the integral of 25z to the second times the group 125z cubed plus 1, and then that's raised to the 12th power. We're supposed to integrate this with respect to z, of course. So we let what's inside of the group to a power. Usually we let whatever's innermost in our function be u. So I let that equal u in this problem. So if I set 125z to the third plus 1 equal to u, then I know that the derivative of u is going to be 375z to the second, and then that derivative will be with respect to z. Well, I go back into my problem and I see a 25z to the second dz. So I know I need a 375. So I just went to my calculator and said, well, 375 divided by 25 is 15. So I would need to multiply the inside by 15 in order to get 375z to the second in order to do this substitution. So I multiplied the inside by 15, which means I had to divide the outside by 15, multiply by 1/15. Now I have my 375z squared dz. All of this is going to become du in the next part. And then I know that this group is just going to become u to the 12th. So I have 1/15 on the integral of u to the 12th with respect to u. The substitution has done its job. It's started with a problem that was hard to integrate and created a problem that's now easy to integrate with our basic rules. We just do power rule. U to the 12th is u to the 13th over 13. I still have my 1/15 out in front. And of course, I have to add the constant of integration. Final answer here, I just said, well, 15 times 13 is going to be 195. So I'm going to have a coefficient of 1 over 195 times the group. Well, we know u is equal to 125z to the third plus 1 raised to the 13th plus your constant of integration. So now I should be able to go in and type that answer in, 1 over 195 times the group, 125z raised to the third, and then we have plus 1. We'll finish out that group, and we know that that group is raised to the 13th. We know that that group is raised to the 13th power, and then we'll say plus our constant of integration. Should be gorgeous. Check answer. Absolutely. I'll bring this down a little bit. So now, when I go to the next question here for number 19, it's asking us to integrate the integral of 17 theta times sine of 17 theta squared d theta. Well, the problem with this, well, there's two problems. I have a product in there that I cannot simplify, but I also have an angle that's not a linear function inside of a sine function. So I'm going to say I need to let u equal the angle on the inside of that sine function, 17 theta squared. Well, I know if I let u equal that, then du with respect to theta is going to be 34 theta with respect to theta. So then I can say, oh, I have a 17 theta. In order to make that 17 theta a 34 theta, I would need to multiply the inside by 2, which means you need to divide the outside by 2. I've done that in this step. From this step to the next, your 34 theta d theta becomes du. Your sine of 17 theta squared becomes the sine of u. So now we have the integral of the sine of u with respect to u. And you say, well, I know that the integral of the sine function is the negative of the cosine function, since derivative of negative cosine is positive sine. So the integral of positive sine is negative cosine. I just go ahead and write my answer as negative 1/2 cosine of u plus c. Then after that, you back substitute. We know u is equal to the group 17 theta squared. So my final answer here, negative 1/2 cosine of the angle 17 theta squared plus c, negative 1 over 2. And we have cosine of the group 17 theta. Now I'll have to use their palette for the theta. So I'll come down here, theta. And then we have that angle, or that theta variable inside the angle squared. We're adding the constant of integration to that. Should be our final answer. We'll check that answer, and it likes it. For number 20 here, this one's actually quite fun. Now, this one could be a problem in which would require double substitution if you only let u equal the angle inside of the trig function in the first step. I could see some people doing that. I automatically knew I wasn't going to be able to integrate the tangent function as is, because I can't think of any term in Calc 1 that I took the derivative of to get the tangent function. So in order to use substitution most efficiently here, it's best to go ahead and write the tangent as the sine of that angle divided by the cosine of that angle. And now I recognize if I let u equal the cosine of that angle, then I know that the derivative of that would be the negative sine of that angle times the derivative of the angle according to the chain rule. So I let u equal the cosine of 5 theta plus 13. du is going to be derivative of cosine is negative sine, keep the angle, times the derivative of the angle. That's where the 5 came from. And then I can say, well, of course, this is the derivative with respect to theta. So I need to see this du in the problem in order for this substitution to be possible, which means I needed to go into the side of my integral and multiply by a negative 5. I did. And that is a legitimate maneuver as long as you divide the outside by negative 5. So divide the outside by negative 5, multiply the inside by negative 5. So now I have negative 1/5 on the integral, all of this negative 5 sine of the angle times d theta, all of that becomes du. So I just said 1 over du, same thing as du in the numerator. I usually prefer to put it out at the end. Now in my denominator, I know that the cosine function is just u. Well, we know the integral of 1 over u with respect to u is the natural log of the absolute value of u. My final answer here is going to be the natural log of the absolute value of the cosine of 5 theta plus 13. And I'll need to keep that absolute value since the cosine could be negative, and that would make the natural log not exist. So our final answer here, negative 1 over 5, and we have the natural log, and it automatically opens up a group. But inside of that group, we must remember to open up an absolute value. And then we have the cosine of 5 theta plus 13 as our angle inside of that cosine function. So now I'll arrow out of the cosine function, arrow out of the absolute value, arrow out of the natural log. Once we do that, we can just put plus c, and that would be our final answer. Pretty cool stuff. If I look at 21 here, these problems are so fun. A lot of them you'll see that they're pretty similar. This one is similar to 19. In 21, we have the sine of an angle, and then I see on the outside of that, I have the derivative of what could be inside of this angle. So I go ahead and I'll let u equal the angle inside the sine function, x to the 11th plus 6. So I know that the derivative of that would be 11x to the 10th, and of course that derivative is taken with respect to x. In order for this substitution to be possible, I must see an 11x to the 10th dx in the problem. I see an x to the 10th dx in the problem, but I don't see an 11x to the 10th. Well, that's why I had to multiply the inside by 11. I've done that in this step, 11x to the 10th dx. If you multiply the inside by 11, you must divide by 11 on the outside. So now this 11x to the 10th dx on the inside, and in the next step, I'm going to replace that with a factor of du. Well, the sine of this angle just becomes the sine of u. So this is just the integral of the sine of u du, which we know is the negative of the cosine of u. I have to keep my coefficient of 1 over 11. That becomes negative 1 over 11 cosine of u. Whenever I plug in the value for u, I just get negative 1 over 11 cosine of x to the 11th plus 6 plus our constant of integration. It's a pretty quick problem. -1/11. We have the cosine of the angle x. Oh, no, not in the denominator. 1/11 cosine of the angle x raised to the 11th. And then we have +6. I'll arrow out and add the constant of integration c to allow you to see correct answer. Up next, this one's similar to number 20. In 20, we had a tangent. This one, we have a cotangent. So I have to remember, I can't think of anything in Calc 1 that I took and had a derivative of the cotangent. So I can't leave it in the form it's currently in. I'll go ahead and put it into the form of cosine of 11x over sine of 11x. And then instead of just letting u equal the angle, I'm going to let u equal the entire denominator, the sine of 11x. That works gorgeously, because then I can say, well, the derivative of the sine of 11x is the cosine of 11x times 11 with respect to x. I don't see the factor of 11 on the inside, so I multiply the inside by 11. If I multiply the inside by 11, then I must divide the outside by 11. Done and done. Now, once you do that, that 11 cosine of 11x dx all disappears from this step to this step and becomes a du. We're replacing that with what it's equal to, a factor of du. So then your inside is just 1/u, since the sine of 11x is u, 1/u du. We know the integral of 1/u is the natural log of u, so I'm getting 1/11th the natural log of the absolute value of u. In this case, I plug the u in, which is the sine of 11x. Once again, I need to keep that absolute value because that sine function can never be negative inside of this answer for the natural log in order for it to exist. So I'll say natural log of the absolute value here of that sine function of 11x. And once we type in that, we just arrow outside of the sine, the absolute value, and the natural log, and put plus our constant of integration. Should be gorgeous. Yes. For 23 here. The work I had for it, right here on this page, I had the integral of secant squared of 5x plus 10 with respect to x. This one is pretty straightforward because I know that the derivative of tangent is secant squared. So I just handle that angle that's not a standard angle of x, and I say, well, what if I let u equal that angle? Then the derivative of u would be 5 with respect to x. I don't see a 5 dx in my problem, so I put a 5 dx as a factor in my problem. I had to multiply by 5 on the inside, so I divided by 5 on the outside. My problem becomes 1/5. This just becomes the secant squared of u, and we know 5 dx is du. Now we know that the integral of the secant squared is just the tangent, since derivative of tangent is secant squared. So the integral of the inside is the tangent of u plus c. I'll have my final answer. I have to remember that coefficient of 1/5 tangent of u, which is 5x plus 10, plus our constant of integration. So I go in here to my solution, just type this in. We have 1/5 the tangent of that angle, 5x plus 10. And then we have plus the constant of integration. Pretty straightforward there. Yeah. The next one here, we have the integral of the cosine of 3x, and we're dividing that by 1 plus the sine of 3x. Okay, so I'm going to let the denominator equal my u in this one. I realize it's not going to be sufficient just to let u equal the angle 3x. That's not going to be enough. I have a sine and a cosine in there, so I'm going to let u equal the entire denominator. When I do that, the derivative of that entire denominator, derivative of the first term is 0. Derivative of the second term, derivative of sine, is going to be cosine of that angle times the derivative of that angle. That's where I'm getting the 3 cosine of 3x and the derivative has been taken with respect to x. So now I can say, okay, I need to see a 3 cosine 3x in my problem. I don't. Well, I can easily multiply the inside by 3 if I divide the outside by 3. So I'll get 1/3 the integral. And then the inside, this 3 cosine of 3 dx, all becomes du. So just like a bunch of other problems we've seen here, the inside becomes 1/u du, which is my natural log of u. Have to keep the 1/3 out in front. This will simplify once we back substitute to 1/3. We have the natural log. Now, I'm curious this time whether or not Achieve will want the absolute value. They should, because now inside of this inside of this natural log function, 1 plus the sine of 3x, it's automatically positive anyway. So we really do not need the absolute value this time, so I'm not going to put it. Wouldn't be wrong to put it, but it's just unnecessary. So I'm going to say 1/3 the natural log of, I need to put that correctly in there, 1 plus the sine of 3x, and then we have plus our constant of integration. That should be our answer to the problem. We'll check that. Absolutely. For the next one here, 25, very easy exponential antiderivative. We know that the antiderivative of any exponential function to a linear exponent is that exponential function divided by the derivative of its exponent. So without even using substitution, I would hope you could just look at this and say, oh, that's just going to be 1/10 e to the 10x plus 5 plus your 10x minus 5 plus your constant of integration. Done. Well, this section is all about substitution, so I showed the substitution. I said, let's let u equal the exponent, 10x minus 5. Well, the derivative of that exponent is going to be 10 with respect to x. I don't see a 10 dx in the problem, so I have to multiply by 10 on the inside, which means I divide by 10 on the outside. Now the inside is going to simplify. This just becomes e to the u, and we know that this part becomes du. Well, the integral of e to the u du is e to the u plus the constant of integration. I brought the 1/10 along since it was multiplying the entire integral. And then our final answer, when you back substitute, just like we knew without using substitution, it should be 1/10 e to the 10x minus 5 power plus your constant of integration. So I'll say 1/10, then we have our exponential function e, and that is raised to the 10x minus 5 power. And then we have plus our constant of integration. Should be good. We'll check that. And they like it. For 26 here, another exponential function, but this one's a little more fun. So now you have an exponential function in your numerator and denominator, but the one that's in the denominator is inside of a group to a power. That should automatically be an indicator that I need to let u equal what's inside of that group to a power, because I can't simplify e to the x divided by e to the x plus 1 to the 8th power unless I do some form of substitution. So I'll let u equal what's inside of the group to a power in the denominator, the e to the x plus 1. Well, I know that the derivative of e to the x plus 1 is just e to the x with respect to x. So now I go back into my problem. My denominator is just going to become u to the 8th. I know that the e to the x dx is just du. So I have, well, that's going to be 1 du. So this simplified gorgeously because I can say, well, 1/u to the 8th is just u to the negative 8th. And at that point, I can use my power rule. Add 1 to the exponent, divide by my new exponent, and then plus the constant of integration. When I simplify this, I'll get -1/7 times u, which I know is e to the x plus 1 to the 7th power, all plus your constant of integration. So I'll go in here and say, well, all right, gorgeous final answer is -1/7 times the group, and we have e raised to the x power plus 1, and then that group is raised to the 7th, And then we have plus our constant of integration. We'll check that answer. Ooh, it's thinking. Uh-oh. Let's see. Did I type something in wrong? -1/7 times e to the x plus 1 to the 7th plus c. Everything there looks good. We'll see here. Did I accidentally put a capital X in here? We'll try again and I'll check that. It looks like I might have. They can be picky. Small x. Check that answer. No. Well, let me pause just a second and figure out what's going on. Okay, guys, as you are watching the video, you might have been automatically seeing what I did wrong. That's silly me. It had nothing to do with the X down there. It has to do with I didn't watch where I was putting the plus C. So the problem was done perfectly, but I typed it in wrong. So you have to make sure you put the plus C at the very end outside of your function. So despite me having the correct answer from the very beginning, it's going to look like it took me 3 attempts just because I wasn't putting my C in the right place. Now you see that that's the correct answer. Okay, now number 27 here. For 27, we have the exponential function e to the 15t divided by e to the 30t plus 2e to the 15t plus 1. What's absolutely critical in this problem is that you understand that that denominator is in quadratic form. Otherwise, it's very, very hard to try to work this problem. So I need to understand that anytime the leading exponent is twice the second exponent and the third term is a constant, that's in quadratic form, to where I should be able to say, well, I know e to the 15t times e to the 15t is going to give me e to the 30t, and I know 1 times 1 is 1. Well, if I took e to the 15t plus 1 times e to the 15t plus 1, I would get out this function right here. Now, the reason that that helps immensely is because anytime I have a group to a power, it sets up an obvious substitution. So I can say, well, now what if I let u equal what's inside of this group to the second power? And then I can say, well, the derivative of what's inside, derivative of any exponential function is that exponential function times the derivative of its exponent. I get 15e to the 15t with respect to t. Of course, derivative of 1 is 0. So now I'm going back into my problem and saying, well, in order to use this substitution, I have to see a 15e to the 15t dt in there. I don't. I see a e to the 15t and I have a dt in there, or I should have it in there. But I don't have the 15 as a factor in there. So from this step to the next, you'll see, well, okay, all he's done is he's multiplied the inside by 15. If you do that, you must multiply the outside by 1/15 or divide by 15 on the outside. Now from this step to the next, the 15e to the 15t dt all becomes du. And so now there's nothing left. You'd have 1 over, this is going to become u squared. 1 over u squared is better written as u to the -2. So now I can use the product rule and say, well, the integral of u to the -2 is u to the -1 divided by -1, and then we have plus our constant of integration. All right, now at that point in the problem, I can say, well, this is better written as -1 over u to the +1 power multiplied by 1/15. I'll get -1 over +15 times u, which is just the group e to the 15t plus 1, and then plus my constant of integration. I need to remember to keep my constant of integration out of the fraction. So I'll have -1 over 15, and we have times the group, e raised, ooh, not capital E, e raised to the 15t power. And then we have plus 1. And now outside of that fraction, I need to add c. And that looks perfect to me. We'll check that. Absolutely. All right, guys. Now, the remainder of the problems, 28 through, I believe this section goes to 36, I believe. I'll do one more video. We'll finish up those and have fun with this section. Hopefully this is helping you out with this section, but at any time, some of these problems don't make sense, let me know. I'll be glad to help.